done. And people joining. Many operations at once. Okay, I'll share my screen. I think we can start. Let's see. Now the webinar. All right. So I suggest we start. Good morning, everybody. My name is Carolina, and I work at Research Innovation Foundation / Institute called Chalmers Industriteknik in Gothenburg, Sweden. And my pleasure is to make the introduction to that webinar. We have the webinar today will be focused on an introduction to additive manufacturing using metals to medical technology specifically. And we have few presenters today we all work together in the European Horizon 2020 project called Manuela. And you will have a short introduction from each one of them. We don't have Edward today, but Lars from Chalmers will cover that part. And if I go to the agenda, so Lars will start with some general additive manufacturing possibilities that we have in the Manuela project. Afterwards, Emmanuel will present one specific case from the medical technology field that we have as the real case in the project. Afterwards, Lars will talk again a bit more general about the different benefits of additive manufacturing in metals and general, and also some different examples from applications in medical technology. And the last presentation will be from Paul. That will be the information about so-called open call that we have in the project, which gives some offerings for different organizations and companies. And at the end, we planned 1.5 hours for everything. We will have time, of course, for discussion, questions, and so on. So if we, and this is pretty much what I already said. So the target today, the aim is to introduce the AM possibilities for medical technology through our project Manuela, and also focus on those specific offerings for companies and organizations via open call. And Lars, you're the first one. So you have to tell me if I should flip the pages, so to say, or if you...
I think you can continue to flip the pages. I will just say that.
Yes.
So, yes, very nice. Happy to have a lot of people here, hopefully. And I will then start to present a little bit what Manuela is. My name is Lars Nyborg. I'm actually a professor at Chalmers, but I'm also the coordinator of the whole Manuela project, which today is one of the largest Horizon 2020 projects in powder bed fusion across Europe. Here you see a little bit of this partnership. So you see you have a number of very important stakeholders. I won't go into this in detail, but I mean it's important to understand that we have end users, technology providers, and a lot of also research institutions that are providing the core facilities in the Manuela scope. So next slide, you know. If you look at metal AM, might be that some of you are very familiar about additive manufacturing, some are not, but I mean, we talk about certain generic benefits of metal AM. You see, and you have seen quite a lot, I think you may be there already and doing a lot of things in this area, that there is possibilities to really flexible product design. And I think we will hear a little bit of things from the product example Manu will talk about later on here from CSM. If we run our process in the best possible way, we have a good material usage that we can transform most of the raw material into final product. Hence, we can have efficient processes, even if they take some time. One of the strong benefits in some cases is reducing the lead times. Basically, that you redesign your products, take away assembly of substructures, etc. And that comes also into the concept that since we're talking about basing and manufacturing more and more on a digital sort of a platform, this means that enhanced product differentiation capabilities that will be there and are there already. Okay, next slide.
Yes.
Adieu, donc ouais, je pense que c'est plus raisonnable d'un coup on se retrouve.
Is the sound bad?
Manu, you have to get
Manu,
muted.
you are online.
Ah, okay.
I cannot mute him, but maybe someone can try.
Okay. Anyway, and then we talk about some key innovations in Manuela. That means that if we're going to have these in a sustainable industry scope, we need to make sure that the metal powder we're using is tailored and recyclable. The scope is that, of course, that we work a lot with these aspects in Manuela to make sure that as much as possible the raw material is transformed into the final product. And that we talk about the pre-industrial testing, etc. for specific products. It's a key thing, right? Yeah. And what we have done, which I think will be explained a little bit more, is we have like a pilot land dashboard. So that should be possible to have a turnkey delivery, one-stop shop capabilities through Manuela. We talk about workflow optimization, automation, making sure that the whole flow of the from start of design to really realizing a product is optimized. That means with qualified products. We work a lot with something called real-time process monitoring. That basically taking the next step in online monitoring of the process. Either it's the laser powder bed fusion or the electron beam melting technology, where we have the latest state-of-the-art technologies put on our machines. So that means like LCA is there also. And then we're coming to the definition of qualification and certification connected to guidelines and really getting the products in place. I think it's important to understand also Manuela is not going to be acting as a commercial entity. It's a pre-commercial sort of test facility that will be offered and will be acting towards users or companies that are interested in technology. Next slide. That means we talk about services. That means there is a hardware layer like any service provider, but we have much more of the material and development context background here inside Manuela. We have the machineries, we have the post-AM processes largely placed through the different actors. So here we are talking about that is in place. But most important is that in parallel we have the whole software layer. That through the anchoring of CSM and MSC software, etc., we have a lot of capabilities here to make sure that we can go fully into the digital world before anything is done in the real world, which is, I think, is really important for getting a success at the end. Next slide, please.
Yes.
And then this is why Carolina is here and Paul is here. We decided here, and that's the outcome towards the commission of the whole project, that we should create a single entry point. And Chalmers Industriteknik is then assigned to be the single entry point for the future sort of action of Manuela. And that means that whatever interest there is to get access to capabilities through Manuela, Chalmers Industriteknik will act as the contact point. But of course, behind Chalmers Industriteknik, there is the whole consortium of the actors, or could be Chalmers, it could be Polito, it could be MSC software, providing solutions for the different cases that will be addressed. So hence this is a key point to understand. The CIT is then going to start as a project office, but will be further developed into more of an agile sort of entity. So, and it will be an independent entity that is not going to hold the resources themselves. They are going to have the resources across the consortium, or potentially outside the consortium in future also. So this is a setup we have created, and we think this is a good way of tuning how to service needs across Europe. Next slide, please.
Yes.
I don't know if I should talk much about this. You will have more details about it, but that means that we have to develop, go through design, optimization, process simulation, everything that is integrated in digital flow. And then, of course, when it comes to testing and analysis and experimental data, then we have the assessment and the realization of the products through the different printers or technologies that are encountered here inside Manuela. Note that Manuela is talking about metal-based AM and only powder bed technologies. We are not working with other technologies inside AM field today. Next slide. There is the dashboard and digital thread management, which I think is a key point, that you say that there are customer coming, that there's a workflow management, there is reporting, so there's a dashboard. And that works then with topology optimization, the actual disciplinary simulation that can be brought in much more here in the next phase here. The post-process orchestration and testing management. So everything this is connected to the dashboard, the digital thread management. And that is the setup, and we are under this development with inside Manuela. And I think we come quite far in this context here. Olivier, one of our experts here from MSC Software Hexagon, is here, and Manuel from CSM in Switzerland is also here, so they can sort of answer more questions in this context here. Yeah. And some resources, we have printers at Chalmers, we don't go into details here, and a lot of capabilities in adding things to these printers. We are expanding with more printers during the year. To be able to handle all metallic materials possible in powder bed fusion, AC powder bed fusion. Next slide. We have a quite number of resources at Polito down in Italy, where there are bigger printers and also capabilities of complementing, and so we have this about the material portfolio. So here you see then there is a lot of complementarity towards the systems, right? So here you have also EBM machines and not just laser powder bed fusion. And the next slide, please. There we have, of course, they can make metal powder, they can facilitate hipping, they have a lot of post-processing, and there are also a lot of instruments, as we have at Chalmers also for polymer-based AM, which in some cases what you use to start with as for prototyping before you enter into applications in the metal field. But just to say that it's there also. Yeah, next slide. And then we have FAU, Airline University, where they have focused very much on EBM technology. So they have, perhaps this is one of the prime places for EBM technology across Europe, with quite advanced equipment, and also, of course, they have application center. They have the whole scope of materials, powder characterization, testing, and also certain in-house post-processing facilities. I don't go into detail here, but you can see that there are really potentially the high stage, quite state-of-the-art here. Next. And they, of course, have a characterization lab, as we have in another places here. So we have the full concept of doing a characterization. As CSM also part of not just doing the design, they're also into the characterization work here. So we have that sort of coupled in many places from here. I don't go into details here, but you can see these are examples of capabilities. Next slide. And right, IVF, a little bit blurry picture, but they are in this Manuela concept mostly responsible post AM process, but they have also printers, and they are working very close with Chalmers, for example, today, and we work close with them. So we are expanding actually capabilities even further here through this structure. So the number of printers that we have access to through the structure inside Manuela is quite extensive. it's also that it's different branding. So this means that we can channel it to different branding here, and that's the key point. That we have the capabilities of selecting the best printer, best options for the potential case of interest. Next. Thank you.
That's it.
It's important to understand that since we have CIT, that's a node entry point. Whatever issues that come up for a case or a use case, then the decision is inside the consortium or inside Manuela to say, yes, this is design that can go to CSM, and with some facilitator inside Manuela, we select where the best solution would be for printing and facilitation of the intended use case. So that is an open question. It's not predetermined in Manuela that we should do things in one place. We are going to do things in the place that makes the solution best, that creates the best solution. So we have like an open structure inside. And that I think is important, that we are not saying that this is going to be there, or there, or there. It's going to be where we will get the things done in the best possible way, connected to the needs that are set up for a specific use case. Okay, thank you.
Thank you, Lars. So now we will have a short presentation from Emmanuel from CCM. On the use case that we have actually in the project and we are currently working on.
So you can directly jump to the next slide.
Yeah.
So I will have a few slides going more into details on tools available in Manuela. I will show what is a typical design flow for a part to be manufactured in additive manufacturing, and I will show the example, the manufacturing of a cranial implant. So go ahead, Carolina.
Yes.
So you already have seen this nice diagram. So we have what we call the Manuela dashboard, developed by MSA software. It's kind of a digital twin of the Manuela pilot line. So we have, thanks to that dashboard, a connection to all the machines that are available in that line, bringing information back to the dashboard. And in the dashboard, we have design tools. So we can perform first a design analysis to study the manufacturability of a part using additive manufacturing. Then we perform design optimization using what we call Apex generative design. So it's topological optimization. So with that, we optimize the mass of the part, the amount of material that will be necessary to manufacture the part. We try to find the best orientation to manufacture the part. We optimize the eigenmodes of the part. We optimize the deformation of the part in the manufacturing process. Once the optimization is performed, we use Simufact additive to simulate the manufacturing process, and if not happy, we loop several times. And then, as I said before, we launch the manufacturing and we follow the manufacturing process. And thanks to all data being collected, we are able to optimize future designs. So it's a continuous learning. So go ahead, Carolina.
Yes.
So in terms of design flow, so first we perform design. So we start from, for instance, in that case, from a bulk part. We define what we call the conditions. We run the optimization algorithm. So you can see that we started with a bulk part, and then we have a funky part in green and red. And we simulate, so you see a nice bracket on the right-hand side. And in parallel, we test and analyze thanks to test sample. We test the manufacturing process. So we see how it will be inside a test blade, for instance. And now we have kind of large amount of experimental data on all the materials that can be used in our pilot line. Go ahead, Carolina.
Yes.
So this is the example of a cranial implant. So this part is really yes, an implant to be implemented as a cranial implant. It has to be manufactured in titanium, and it's kind of thin, so it's 1 millimeter thickness. So we perform several optimization. The main goal, so you see the produced part at the bottom with its support. We perform several optimization, mostly to minimize the deformation during the part manufacturing, as the part is really thin and it has a weird shape. It is really prone to deformation. So we had to optimize the orientation as well as the number of support to be able to produce a part within specification. And as you can see on the right-hand side, several test samples were produced to analyze the material, and we produced test blades to study the deformation, and right now we are within specification. So the final part, we have just launched the final manufacturing of the part. Go ahead, Carolina.
Mm-hmm.
I think that's it.
That's it. Thank you, Manu.
You're welcome.
So let's see. I think we can keep the questions maybe to the end, at the end. But now you've seen one case that we have in the project. And now we are back to Lars to talk a bit more about different types of AM and characteristics and some examples, even more examples from generally medical technology field.
I hope that will add further, and of course, please feel free later on to discuss with Manuel and things like that, because he has done could perhaps share some details on whatever possible on the work he's doing. I mean, all of you may know that if you go back to standards about what is additive manufacturing today, if you go to ASTM, you categorize this into 7 process categories, and it might be that you are aware of something that called, for example, fused deposition modeling, and that's it go to polymers, and that will be in the category material extrusion. So if you go to the standard, we talk about 7 categories: binder jetting, directed energy deposition, material extrusion, material jetting, powder bed fusion that we are talking about here, sheet lamination, and vat photopolymerization. The last one is basically lithography. And of course, some of these technology can be used for polymers, some of them can only be used or preferable for metals, and in some cases we can actually process ceramics also. But now let's talk about powder bed fusion. Next slide. Powder bed fusion, as you know, this is a little bit basic, but I think you may know it, but I just treat it anyway, so you understand the basics. We fuse material, and that means that if you have fusion material to fully dense material from a powdered material that we start from, it can be metal, polymer, actually ceramic powder. The technology is a little bit different depending if we work with metal polymers and ceramics. Now we will talk about metals. It's actually the most growing technique today. We use laser, electron beam, and of course electron beam can only be used on metals. We need to have support structures, as you saw a little bit of the case Mana was talking about, since we need to have them for structural support and remove them later on. And there's a lot of tricks to make sure that you use that and design it in an efficient way. From a material point of view, we have what we call anaesopha in metals. That is, we have a certain grain growth, or we have certain capabilities that the properties might be different in the build direction compared to across the build direction. So then one has to take that into consideration in some kind of designs and specs. Typically, we may need some post-treatment, could be heat treatment in some cases, if we try to avoid it, because the more we can go without needing heat treatment, the better. In some cases for aerospace, so hot isostatic pressing is there to really reassure defect-free materials, even if nominally you're building fully dense. It can also be so that it's one manner of qualification, certification, that you use certain post treatments after the printing. And also freshing surfaces in different ways is part of the game, okay? Mm-hmm. Next. And if we laser particle fusion to give the metal, it's in protective gas. We have a lot of work now that we do to develop this, how the gas can be done. I can tell, for example, at Chalmers, we have a PhD defense later on by end of March, where we have done a lot of work on tuning different gas compositions to actually take the advantage of the gas itself for improved processing. The size you can go to, depending on machines, 800, 400, 500 millimeter. There are quite good variability of materials, even if you go and look on the equipment providers, how much are commercial, but there is a lot of in-house development also. Decent reusability of powder. You need fine powder. You need to have powder that is in a 20, 80, 20, 50 micron range. And that means that by laser powder bed fusion, you really can create small channels and have finer surfaces compared to EBM technology that we'll talk about in the next slide. Modern techniques today can use a number of lasers in parallel, say up to 4 or more lasers. That increases productivity. But we can also boost productivity by working with greater layer thicknesses, as we do inside Manuela, which increases productivity by 3 or 4 times compared to the standard processing parameter settings. Next slide. So, of course, if you look at the material, it has to be understood from a material point of view. If I take built like in the laser powder bed fusion, the microstructure material becomes unique. It's not the same as a caster material or as a wrought material. There could be certain anisotropity in a build direction, but typically it's important to know that we have our process under control. We are building basically fully dense materials. But it's also important to understand, at least in a laser powder bed fusion, it's a rapid solidification, rapid cooling technology. So the material will locally always undergo a cooling rate on the 10 to the 4, 10 to the 5, 10 to the 6 Kelvin per second. That is what's happening. So of course, it's material that is built locally with very, very, very high cooling rates. That is the inherent in the technology itself. Next slide. However, does that matter? Well, the interesting thing, if you look on the 316 stainless steel here you see example where we have used what is standard atmosphere argon, 800 ppm oxygen and 20 ppm oxygen. It's a little bit where you have this type of specific oxygen control during the build. Now, stainless steel is usually what we say easy to build material. And what it is important to understand there, if you look at the properties, this is built good in all these conditions, and we see that the tensile strength, yield strength, they are actually similar, even better than wrought material for established materials and process. So it's important to understand that the performance of the material, at least in this particular case, is not worse expected if things are under control for at least static properties than if you would have a wrought material, the conventional manufactured part that you machine into shape. That must be understood. We talk about quite good performance, mechanical performance. Okay, next slide. However, if you go in details, I'm a little bit too materials oriented. You can have certain elongated grains in building direction. These are so-called EBSD maps, but a little bit smaller grains closer to the surface, and you see that there is a surface roughness, so there could be random orientation. So it's very important, that is, if you go back to the work done by Manu and CSM, that you go into the design component, you really need to take into account the AM microstructure, that it is specific, it has its inherent characteristics. So this is something we have a lot of knowledge about inside Manuela. Okay, next slide.
Yeah.
There is still a number of robust powder for additive. If we go to equipment provider, this is the list they would give you. So around 20, 30 alloys. There are certain further development. There are a lot of in-house development. So of course, if you go to medtech sector here, of course, you have the TI64 there. That's really established, and interesting to see that it's established also when it comes to EBM or powder bed fusion, electron beam melting. So hence, at least for medtech applications, we have materials in place that should be able to tick and be working for a lot of different applications. This is important to understand. However, we still lack the broad scope of materials. That should be known. If I would say, I take a part and I do cast it to have a wrought, and I say that the material portfolio I have there, if I machine something, is completely different. But that should be understood. Okay. Next slide.
Right.
What we have inside, which I think is a really important things, that is we have, for example, quality assurance and latest models. This shows the sort of online process monitoring for laser powder bed fusion, where you're actually using the interaction of the powder bed with the laser and capturing the reflected information that you do. You can do a powder bed. This is imaging in a powder bed. You can have an optical tomography where you had the integrated melt emission at a certain wavelength, or you can have a sample the melt emission in a variation of wavelengths. That means that we can locally, with the resolution of sort of the laser beam, capture what happens in real time. So once we're building something here, we collect gigabyte of data that can be treated and used for ML, AI, or any sort of a potential algorithm post-mortem, or potentially in future also inline feedback loops. This is important to understand, and it adds a certain element of quality control that is not normal in all cases. Next slide. One example is in with the research. You see that there need to be AM design that is for robust powder recycling. If you have what is called verge, and there's something called sputter, and if you reuse, and this is research a lot inside Manuela. So when we get the powder into our processes, we have a pretty good understanding of what mechanisms that are there and how to handle or how to mitigate things that can reassure a robust powder recycling. And that is of course important to the end when it comes to cost and certification and qualification of real parts in both prototyping, first series, and later on. So the technology is there to really make sure that we have this under control. Okay, next slide. EBM is a different story. As you know, EBM is quite much something that was or electron-based powder bed fusion, or also electron beam melting, which is the first starter voice coming from Arcam G additive. Requires vacuum, of course. It's only metals and alloys. You see something on the build place, quite decent sizes. Some range of materials, rather robust, particularly application in biomedical aerospace, and we have it inside the Manuela. You see titanium, TI64, cobalt chrome, yeah. as you know, here you do pre-sintering on the powder bed. So the powder bed itself is an anchoring, not just support structure. That means there's a little bit less recyclability of the powder. And of course, since you do like this, there is not necessarily exactly the same design possibilities to create small channels, for example. So you say the laser technology and the electron-based technology, they have different pros and cons, right? Yeah. One of the pros for EBM is that the build rates are, since you use an electron beam, are inherently always much faster than a laser beam, because a laser beam you use optical scanning and something. This is electron beam. Electron beam can always be scanned much faster than laser beam. That's in the technology itself, right? Yeah. So next slide.
Yeah.
And there's some manufacturing readiness levels. I think we jump this and go back to the next slide. This is from Edward. So you see this, if you go to Curtis or ARCAM, a lot of you know that in the medical sector, there are two scopes. You talk about standard implants or customized implants. This is well established into the medical sector today with EBM, and of course, I think the interesting thing here is to tune this into customizing. Of course, this means that if you have a surface like the Curtis of Arkham here, G additive, where you have not a solid first surface, but that you really create more like a control process in the surface. It is something that you say, well, where do you want your surface to be like this, and where do you want your surface to be polished in a biomedical application? This is an inherent possibility with the process, as you know, and this is something to consider. Yeah. Next slide.
Mm-hmm. Oh, sorry, there was one more.
And that is, of course, the Curtis Arkham. This means, of course, as you know, you can tune your builds here, and this is just like this bionic structures that you put into like a replacement, of course, and then of course the bionic structure, as you know, can be designed to have the weight optimization that is fitting for the particular case with the particular design limitation of its dimensions. So I mean, how would you manufacture this in a proper way if you did not have additive manufacturing as the enabler? I don't think you would do it in an efficient way. Next thing, of course, if you look on work that we've done on together with Gothenburg University, then you look on designs and fabrication. You have all these things that you can really go for customized implant, both from the geometrical design, but also compared to how you will need to set the surfaces in different places. You can also start to work, as you see in the lower end here, you optimize your struts, so to say. So it is a hollow structure. This is possible with additive manufacturing. So inside, of course, you don't make a solid structure. So tune the sort of mechanical performance, so stiffness and stuff like that on the structure or geometrical structure can be fitted to what it needs to be done, right? Yeah. And still having it into the design space in a proper way. And perhaps you understand what Manu showed before, that this is one of the intrinsic capabilities of additive manufacturing. Here we talk about EBM technologies, but anyway, or it can be laser also. Yeah. Next slide.
Yeah.
So then, of course, where can it be? Yeah, you see this product sample that was discussed a little bit before inside Manuela. You know that there is a dental application. You can use tools. I mean, it can be sort of that we need to have customized tools that we manufacture, pre-operational or customized implants there. So there's a lot of different application here where I would say the customizing and design capabilities compared to quality control of the process is the key enabler for medtech applications, I would say. Yeah. Next slide.
Yeah.
Market. If you look on dental, the dental sector, as this is a scope we did, dental instruments is around $6 billion today, and dental consumables lies today about $25 billion across the world with AM as the enabler. You can see that It's consumables, if you look on this, and it's also instruments or that is part of the game. And you see a little bit of the relation here. Okay, next. If you look another thing, you have digital metal, in Sweden. This is not powder bed fusion, it's the binder jetting technology where you can go much finer in dimensions. And it's a two-step process where you first do your printing with the binder, remove the binder, and then a second stage process where you sinter the material together to the necessary density. Of course, it has certain pros and cons, but the key point is that you're using much finer powder, normally sub 20 microns. So the surface finish and the products that you can create are a little bit on a different scale, right? Yeah. Next slide.
That's it, Lars.
Yeah, that's amazing. So this was a short scope, and probably most of this was known to you. But my message here is then it is that we have two technologies, the EBM, the laser powder bed fusion. They have the pros and cons. We have a lot of material knowledge behind what we do in Maniola. We have the whole digital setup that was presented by Manu. And that means that you understand that we have this scope that is the design connected to the capabilities. That is the key options here. I would say that, of course, at the end, it needs to be cost in place. It needs to be performance in place. But that is also part of the game to make that happen. But I mean, of course, we are talking about doing things that are not necessarily the same as what you have going to normal service provider. There's another sort of structure behind here inside Maniola. I hope that is evident from the presentations we've done here. Okay, thank you.
Thank you, Lars. So now we have the last presentation for today about the open call that Paul will present.
Okay, thank you. Well, I will actually connect directly to what Lars finishes with, and he said that the point with this opportunity in Maniola, which we call the open call, is to give the possibility to companies or to other organizations that have some kind of interest in this technology and this process. But the point, as Lars pointed out, is not that we should compete with commercial companies and their offerings. So what we offer from the project is the possibility to use the project's assets as a prototype line. So we will support you with whatever you need in order to, first of all, just try out if your product or your idea is suitable to be processed in metal IM. And if it is, we can also help you with the different details of the complete process when it comes to both design and manufacturing and post-processing. So once you have set up your product, we can verify that it is working. You will go outside to actually print your product in a commercial line somewhere. We're not going to be the producer of your products for you, but we will help you set up so that you know that your product is good, that your business case is good, and that everything can work. So this opportunity in the project is offered. This is a very key aspect of the project because the European Commission really is interested to see that everything that is coming out from the research is also utilized in the society in some way. So this is why Chalmers Industriteknik is included in the project, and we will be your interface and the interface with industry. So this open call within the project is targeting all the European companies and the associated countries. We will select 10 different business use cases, as we call them, in total to be implemented in the project. And we will co-fund each use case 50%. So we define a budget, and the project pays half of it. If you're interested, if you think that you have something that you would like to try, you make an application through the portal that is on this PowerPoint slide. It doesn't have to be very complex, but you have to apply through the portal. If you don't know how to manage in the portal, we have a help desk that is available so that you can manage to get your application through. So please, next slide. We will evaluate the proposals we get, and it's important that you have clear ideas about your concept and the level of innovation, impact and market potential, and that you think that we can see that the ideas around implementation are good. But it's a quite simple evaluation, I would say, of the proposals. So please, next slide. The open call is open at the moment. We opened it 1st of December last year. We will make 2 cutoffs. The first one is end of March this year. We will select 5 use cases for implementation. The second cutoff we have end of September, where the last 5 use cases will be selected. If you are one of the winners, then we will notify you directly and start to plan the implementation together with you. And that will be Chalmers Industriteknik that will contact you. Our planning is such that the 1st of November 22, we must have processed and closed all the use cases, because that is the schedule of the project. So please, next slide.
Yeah.
So as I said, we are the interface with the company at Chalmers Industriteknik. We project manage the implementation, but we take the resources from all the different partners in the project. So when we implement your use case, we will develop the normal set of documents like the requirements, specification, process flow charts. We will allocate resources, make a budget, and set up a contract together with you, so that we know you can be confident about the delivery dates and the budget and so on. And the planning tool we use is called Project Place. So please, next one.
Mm-hmm.
Okay, so that was in a nutshell the open call. If you're interested in the open call, you can either just go directly to the homepage or to the application page, or you can contact us because the call is open, so it is time to act for you if you're interested. So here we have some contact details. You can send an email. You can also look at our homepage for more information if you want. Okay, I think that was it.
Yeah,
about
that was
the open call.
Thank you, Paul. And just one thing I forgot to mention, but I will send out this presentation, if you'd like, to everybody who participates here. So both the recording of the webinar is available, and also you will have all this information in the presentation provided. Great. So that was the part of the presentations. Now we have still some time for questions and comments or general discussion. So the floor is open. Is there anybody who has some questions for the presenters?
Olof here, can you hear me?
Yeah.
Yes,
Mm-hmm.
I just have a question to Lars about, you were talking about the extreme cooling rate, and that was part of the physics and I mean the basics of it. But could you just explain? Is that like a good thing, or do you wish a slower cooling rate, and how does it work?
Is Lars there? I cannot see, but
He has.
I was shutting off when the other Lars is here. Do you hear me? Yeah.
yes.
Yes.
Yeah. Yeah, it is a little bit different depending if it is the EBM or the laser that you're using. EBM, then of course it's important to understand the cooling rates are not as high, because what you do there, you use the electron beam to sinter a powder bed around the part that you're building, and hence because and that means that stress distribution and things are completely different and less in EBM actually than in laser. Because you keep your material at a certain temperature by the electron beam. You actually rapidly scan it around and loosely sinter powder around it. But still, it's rather rapid local cooling. If you go to laser, yes, it's a rapid solidification technology. And that means that you create a unique microstructure, basically cellular structure with but it's not a drawback. It's actually potentially a benefit. Because what we see here is that of course you need to consider that there might be a stress distribution. That's why, for example, if we have a Hexagon MSC software here, they have a software called Simefact, where you can model this for a whole part beforehand, and you can tune whether you need to redesign or reorient and position your part in the proper way. The key point is that it also gives you the fact that from a physics point of view, it's a local, it's not the whole. I mean, it's rapid. It's like having a welding process that is localized in a couple of 100 to 200 micron and repeating that with some speed over a whole build. And actually, it is good, I would say, because we see that this is one of the reasons why the properties can be better than a wrought material. So it's actually interesting from a physics point of view, metallurgy point of view, if you understand what I mean, that we see that we can create unique microstructures, and we have perhaps not thought about that so much, and perhaps it's too much research, but we can really make material that is behaving potentially better also combined with the design. Do you get my point? Yeah.
Thank you very much. Yes, I was before your answer, I was unclear about the benefits or drawback, but now I understand much more. Thank you.
You can look on the stainless steel. The stainless steel, if you build it, will have a yield strength that is higher in normally quench anneal conditions. So why? You can say that it's almost like have you done a little bit strain hardening of the material, as it has comparing properties like cold formed material as printed condition. Okay. So, and then of course it's a matter of how you do the heat treatment, stress relief level, but what we see is that we can really have much better properties than you expect. But you have to have the process under control. That's the key point. You need to understand that how you build fully dense material. That's for sure, but that's the process control itself, right? Yeah. Okay.
Thank you.
Thank you. I have one question. If anybody has questions regarding design or simulations, I just saw a message that Emmanuel has to leave in a couple of minutes. So if there are questions to Emmanuel on the topic of design, it's your chance now. No one has anything there? I mean, you can always reach out to us as well afterwards. Okay. Any other questions regarding open call or generally additive manufacturing or metals part or project?
Hi, good morning. I'm Casas.
Hello.
Yes, I have some questions. Indeed, I wrote quite a lot of them. It's not indeed due to design, but more or less. I was asking myself, what about cleaning, the cleaning process, the things with nanoparticles. I have also one question about biocompatibility and the whole thing with nanoparticles, how to prove that the implants indeed are biocompatibility, how to clean also these rough surfaces, as you saw already some pictures, how to clean those.
Mm-hmm.
Do we have this is Lars here. Do we have anyone from RISE involved here in the meeting, or?
I don't know if they participate.
I mean, but I can give some comments. First of all, when you printed your part, I mean, depends on the process. The laser, we go down to less than 10 micron in surface roughness. That's possible by the scan strategies. The EBM is a little bit coarser because of the inherent stuff in it. Hence, what you do, you clean off what loose powder is. You do blasting, you do differentiation, and then there are also specific post-AM surface treatments that start to be in place, like you call characterization or things like that. We have electrochemical treatments of the surfaces. So there are a lot of cleaning procedures that are around here to try to reassure the necessary surface specs that you would have for a certain application. Is that the answer to my question? So I mean, we're not talking about having, and in some cases it may be that you have an outer surface where you say, yes, this outer surface, I need to have it very, very, very low surface roughness. And then what you do, you integrate a little bit small machining allowance in the design. If you have accessibility to do a machining operation. So your design is then set that you say, yes, I need to add 0.1 millimeter or something into my dimensions, because I know that I need to touch that surface in some sense to have it under control, as long as it's possible to have access with the second post-AM. So that's part of the design procedure. Is that okay to answer? So.
Yes, one part of that. The second part was indeed with the examples you saw us with the implants. So like a cap with some fine surface to, I think, to anchor, especially in the bone. How to clean those? I mean, this is really. No, I think it's one or two before of that one. Yeah, perfect. They were there with the air cam. Yes, yeah. The air cam, for example, I think is quite challenging.
Are you especially afraid of nanopowders, or what are we talking about?
Yes, I mean.
But depends on how we clean it. I mean, it's of course it needs to be there are mechanical cleaning and chemical cleanings that you apply to. But the key point is when we build this in EBM here, then you have a normal size range 40 to 80 micron. So you don't normally have any dust in it. Of course, you have to reassure that your size is there. So the powder we are using should normally not have any nanopowder within it.
So indeed, how to clean the implant from the powder? How could we be sure that, for example, this cap could be clean?
Yeah, but you do a lot of mechanical cleaning, or sort of you blow away powder as much as possible. You blast it if it's possible here, but here you need to blow it away, right? Yeah. But the key point is here is also that since you are doing, I mean, this is more of the courtesy of ARCAM. So details, they have established a cleaning procedure for this, and so this is industrial production, right? Yeah. So perhaps we can address that question to them. But basically, you have a cleaning procedure. You reassure these cups are put in your bodies right today. There are millions of them in your body today. So it's not pre-development. It's actually existing industrial applications. Yeah.
So I think that then the answer is just to find a cleaning process and then validate it for its design.
You need to validate it for the specific design, and you need to validate it for the application. So you need to reassure it. So I mean, that of course is something that you have to set as a precondition for the potential use case that could be of interest, and say, yes, what are the requirements and so on. And then this has to be part of the potentially developed solution, I think. Yeah. And I can't say that it is one way or another way. I think it will be use case specific. Yeah. But there are technologies. Yeah.
Maybe sorry, I can just step in because we maybe didn't explain so much in detail, but I'm just flipping, sorry, the pages quickly. because we talked, we presented like in the project, for example, sorry, I'm just going back here. When we talked about different technologies, but actually our colleagues at RISE here, well, we present here their printers, so to say, but in the project, this is the entity or the facility responsible for all post-processing. So all our printed parts go before they are sent to customers, for the removal of those support structures, for any blasting, 3D scanning and everything, they take care of that. So the technology, all this cleaning, removal of any powder that would be left is done here. We just didn't present all their post-processing or machining possibilities, but in the project it's all secured as well. So I just wanted to make one comment there. Yeah. So
I don't know if it's going to come more questions. I have indeed in that way another question. How to validate a process? As much as I know, as a company, we have to also to keep an eye on all those processes, which parts to be validated or checked in the 3D printing process. And at the time, if you want to lose also one word about the sterility and what happens after the part comes out of the printer, and you want to keep indeed this sterility status.
I'll try to understand. This is Lars here. I mean, the procedure we set up here, if you look on the cranial implant, we do the prints. There's a lot of development work, as Emmanuel from CCM was talking about. And when we do this, we take all the powders in, we print so-called witness samples that is then processed in parallel with the actual use case to certain properties and performance and all the specs that are required. And then, of course, it is not a serial production. That must be understood. It is to the first stage to bring to someone that can take it further, say, yes, with this type of solutions, we can go and take the next steps in industrializing a solution. That's the whole intention of it, right? So then, of course, we are not going to make huge number of parts, but it has to be good enough, or it has to be qualified, so it can be seen that this can be run in a more developed procedure in the next phase. Is that the answer to my question? I mean, and that depends on the scope of project or use case. There of course can be wide ranges of different services. I don't know, Manu, if you have something to say.
I think Manu had to step out. He's not here.
Yeah, but this is what we can take a separate discussion on that one. Where I can bring other people into this, so I don't talk on behalf of other people here. I'm sorry. I just give you a sort of direct feedback, but then I can talk on behalf of other people. Then I will bring people from the team in Manuela into more of detailed discussion with you about these different aspects. That would be the most appropriate way to go take the next step. Is okay?
Yeah, thank you. I was just thinking on some parameters of the 3D printing. It could be freeze, and then those parameters could be validated, and then from the company point of view, then we say, okay, we can rely on these parameters, and then we can validate them as a validation.
Yeah, I understand. I mean, it's very important to understand the following, right? Yeah. Say that you have a certain design, you're going to print the part, and this part is the one we develop the design for it. There's a material selection that is done, it's qualification of the powder that is there, everything that's put in place. Yes. And then what is then, you decide that, well, this is going to be printed on EBM machine, or it's going to be printed on a powder bed fusion machine. What we have to also understand that this is you basically to have this validated, in most cases you need to decide, yes, I'm going to print this on that laser powder bed fusion and also that brand and that type of machine, right? Yeah. So that's the first thing you need to do. You always have to sort of lock as much as possible. And then what we reassure is that there is a broad processing window, that it's allowing you to have a certain flexibility in processing parameters for the print, because it's a matter of understanding how big this processing window is. So that means that there is a potential variability of the setting parameters still getting a qualified part, because that needs to be there depending on the design, since you can have hotspots and different stuff in the design, that you need to allow certain changes in this. And you have to also understand where your weak sort of locations will be, where you are the driving forces or the limiting factor for your critical design. So once that is, then you lock the whole process. And once that process is locked, this is the way you should manufacture it, right? Yeah. It is like that you do all the pre-development, say, yes, with these processes, a potential of these product family machines, this is where I'm going to do it, right? To have everything in place. So that means that the AM is still have a problem to go from, I would say, vendor A to vendor B. You get my point? If you are, so that will not necessarily be solved here. You can have some kind of ideas. If you go from using, say we developed this thing for a machine that comes from vendor A and everything is in place. Yeah, if I don't want to transfer my solution to vendor B facility, will that work out? That is always an issue to consider, and because you qualify things and lock it as much as possible, that is a must, I would say. Yeah.
And my last question was about sterility process. I think that the 3D printing is quite a sterile thing, or can be made sterile, and how to keep this status after the sterility, after the 3D printing. Do you have some ideas how could we work?
I can look into this. This is Lars here, because we work together today in different projects with the people in the biometals field in Sahlgrenska University Hospital. So I can couple these guys into this. They have been working a lot with additive manufacturing. So say that we go into biomed here, it might be that we really anchor in some competence in from that field to support us with that. So I would not like to take an answer directly, but we have the networks to bring them in. Well, once you could be interested here. Yeah. I have direct contacts with the people working with different kind of studies today. Yeah.
Thank you.
Okay, thank you. Good questions. Are there any comments or other questions to anybody? We still have some time left, so don't be shy. No, it seems everybody's happy. Any other comments from the presenters?
No.
No? Okay, good. Then I think we are done for today. As I said, I will take all the addresses. All of you who got the invitation, I will send the presentation as soon as it's in PDF and so on. And thank you so much for your participation today. Very interesting discussion as well. And don't hesitate to reach out when you think, you know, the open call is something interesting, if you'd like to learn a bit more. And yeah.